Okay, so today we're going to do electronic spectra. I'm also going to consider line profiles, which you talked a little bit about yesterday, but I'm going to go through a little bit more formally. So just to remind you where we are with molecular motions, we've got the rotations, we've got the vibrations, and then we've got the electronic motion. And that's what we're going to do today, but they're complicated because you don't get the electronic motion on its own, you get the rotations and the vibrations all at the same time. So these spectra have a lot to consider. Come in, come in. So you end up considering all the motions at the same time. What it means is we will today only consider diatomic molecules because I want to keep things within bounds. Polyatomic electronic spectra of polyatomic molecules can get very messy. Oh, that's a big improvement. Right, so electronic spectra. So when I said that yesterday that vibrational spectra are often called infrared spectra, electronic spectra molecules are often called ultraviolet spectra, but actually they don't all necessarily lie in the ultraviolet. In fact, I have a student project going on at the moment on NH+, and the separation between the ground state and first excited state of NH+ is 500 wave numbers, which is about one vibrational motion, but that's very unusual. So they do normally lie in the ultraviolet. However, some astronomically very important species, such as TiO and VO, titanium oxide and vanadium oxide, have strong spectra in the near infrared red region. And that's what makes them important, because that's when you have the peak flux from an M-dwarf star, which is the sort of cool stars you get molecules in, they lie right in the peak flux. So they have a really profound influence on the structure of the star. And it's also considered they're important in exoplanet spectra, atmospheres as well. So obviously, if you're doing electronic spectra, it involves changes in the electronic state. It involves changes in the vibrational state, of which in principle any are allowed, but there's something called the Frank-Condon approximation, which I've already alluded to, and we will go through in a few minutes, and if not derive, at least discuss in a bit more detail. And then you get the inevitable rotational selection rules, which should be etched in your brains by now, that delta J is 0 plus or minus 1. And 0 is quite common. Half the bands have Q branches, half don't. So to give the selection rules a bit more systematically, so this is the equivalent for electronic spectra for molecules at the tables we've seen several times for electronic spectra for atom, that the rotations are delta J plus or minus 1 if lambda, I'll come to what lambda is, what these quantum numbers are. If lambda is not 0 to 0, any vibrations effectively spin 0. You do get some metastables. Why am I getting feedback? I've been getting feedback on other days. Maybe I'm just standing in the wrong place. I'm getting a bit of feedback. Anyway, okay. Basically, we only need to consider delta S's 0 transitions. There are some examples. Actually, the most prominent one is oxygen in our Earth's atmosphere, where the ground state is a triplet. The first two excited states are both singlets, and they're metastable, and they do decay down to singlet, or they do absorb upwards to singlet. But 20% of the atmosphere is oxygen, and the lines are still not optically thick going all the way through the atmosphere. So that gives you some idea how they weak are. You get 0.2% of the atmosphere in water, and you completely blanket out regions of the atmosphere, just to give you a contrast. So they're there, but they're very weak, and we're not going to consider them in detail. So lambda, which is the projection of the orbital angular momentum, that can change by 0 plus or minus 1. That's the same as the atomic rule, effectively. And then the various rules on sigma states, which we'll come back to in a minute. So as I said, the Frank-Condon approximation for vibrations. So let's deal with that first. So There's my pen. There it is. So I left myself a blank bit of paper here so I could scribble. So the basic rule of the Frank-Condon approximation is that you need to take the square of the overlap between the vibrational states in the two states involved. So we've got a picture here, and I drew these rather worse than they are on the picture of the low-lying vibrational states in the ground state. So the ground state, which is just a nice hump, and then the different nodes going up through. And what you do is you project that on the vibrational states of the upper state. And actually, so the real expression for the intensity, and that's, I should be more accurate here, it's proportional to the square of that number. So the transition intensity is, and this is basically a general dipole integral. Effectively, we've already written it. It's just that when we're using the same electronic state, that cancelled out. When we're using the same vibrational state for rotational spectra, that cancelled out. So this is the same integral as we've had for all transition intensities. So you write it like that. And what Frank and Condon said was that the dipole actually comes from that integral. So that gives you your transition dipole. Is an electronic dipole. And basically they said it just comes from the single value at equilibrium. So basically it's the value of the dipole at this point. And then you get, if you do that, you then get I equals that dipole squared times an integral. And sorry, I've been using Dirac notation periodically because it's so much more compact. I hope people understand. You get a overlap of the vibrations, and you get a similar thing for the rotations. And the rotations are represented with just angular momentum rotation matrices. So this is just an exercise in angular algebra, which I don't propose to go through. And they're called Honold-London factors because Honold and London first worked them out. But they're just numbers. They actually give you your selection rules, basically. So they're the numbers, because the dipole, the angular momentum of the dipole is 1. So J and J prime can only differ by 0 plus or minus 1 because of the rules of angular momentum algebra. And I suspect many of you have not done that level of angular momentum algebra, so I'm not going to go through it here, but it's where they come from. So you end up with this integral here giving you this factor. And I'm going to clean this in a minute because I then want to draw some pictures. So just wait till people are writing it down, just wait till you've written it down. Okay. So you get a number of situations. You get one situation where the two potential energy surfaces are completely parallel, like that. And if we just consider the case where everything is in the vibration, if you're considering absorption, most things are in their vibrational ground state. So we'll concentrate on cases where in the vibrational ground state. If the two potentials are completely parallel, then that integral is approximately 1. So basically all the transitions go to what's called, and this is then, be more specific, the integral naught prime to naught double prime is practically one, and that band is, in the jargon, is called the naught naught band. And you do upper states first, so that's V prime, V double prime, that's the 0, 0 band. So this transition from no, it's not marked here. The one from here to here will be the 0, 0 band. So in a case where the two potentials are nearly parallel to each other, you get dominated by the 0, 0 band. That's not that common a situation, but actually if you get what are called Rydberg states, you get an ion, and they have lots of parallel states, you get something like that, you get completely dominated. So you may, in that case, only have one bright vibrational state. We have here, already on this picture, quite a common situation where the excited state potential is less strongly bound than the ground state potential, so it moves further out. And that's quite a common situation because you excite what will be a binding electron, so you weaken the binding of the molecule. So you tend to go to the inside bit of the curve here. And if it's really extreme, if this potential actually is here, then you go up right to the edge, and you go up to classical turning points. So one approximation people sometimes use is actually that everything just goes on the classical turning points here. And that's true when the potentials are strongly displaced, like this. So you go naught to V quite high in that situation. Because the projection, if you're here with your ground state, the projection onto here is just 0. There's just nothing there. But if you go here, you can see it maps quite strongly on. You get spread across several states like that. And then, of course, there's another situation where your ground state potential may be out here. And you could do that. That's less common, but it's not unknown. NO does this because actually when you remove an electron out of NO, you increase the binding in the molecule, not reduce it. So the upper state is more strongly bound.
Yeah. Excited state basically it's further away from the...
Yeah, so the most common situation is one drawn in the original picture I've scribbled all over. And it can be even further like this. And obviously you have a range, I mean I'll show you some pictures of electronic states of diatomics. You have a whole range of states and they don't all necessarily, so different states may follow different rules. But that's basically how it goes. So this is what I call a propensity rules. It tells you what's likely to happen. It's not a rigorous selection rule. So indeed, moving straight on, I think I've got, oh sorry, I have to do this first, didn't I? So here's an example of calcium oxide, and one below is aluminium oxide. You can see here, the displacement between these is really quite high. So for this, well, okay, it's a triplet, so you probably won't get to it, the first singlet here. But even going up to singlet, you're going to go up to relatively high vibrational states. And actually, experimentally, one of the results is you get a you get an electronic spectrum like this, and they don't know what the vibrational states are. They think this could be 4, 5, or 6, for instance. They don't actually know which one it is. And because it's theoretically quite difficult to get these gaps really accurately, in principle, you can calculate it and tell them it has to be V equals 4, because otherwise it doesn't fit energetically. But in practice, you quite often get errors in your excitation energy, the same magnitude as one vibrational spacing, particularly as the upper space vibrational spacings tend to be smaller because the potentials tend to be more broader. So that can be quite a common problem. And in fact, when we did a line list for calcium oxide, I was talking to people about master's projects. We gave that to a master's student to do. First student didn't do very much work and did a thoroughly bad job, so we gave it to a second student. Second student worked very hard, but the results weren't very good. Third student worked very hard and the results still weren't very good, at which point my colleague Sergey took it on board and realized the experiment had assigned all the lines incorrectly, so you couldn't make sense of it. So we had to completely reassign the spectrum. And it's because this is quite difficult to do this sort of thing. And you can see here, the potentials will cross each other. And that was causing strange things. And they just actually assigned transitions, not just the wrong vibrational state, it's the wrong electronic state. So it was a real mess. So the second two students did honorable attempts at trying to get it to work, but it was just very difficult. Aluminium oxide. It's not a great picture probably for looking at, but these are all, that's a doublet sigma, doublet pi, doublet sigma. So these are all allowed transitions. And you can see that here, firstly, that the gaps are not very big. This A to X transition is very well known in plasma physics, for instance, aluminium plasmas. But you can gain, you're getting the things where you're going into the off the center on the vibrational levels. So what I want to do is talk you through the rather strange notations here. So these electronic states have a label, and it is sort of like the atomic label, but it's a variation on it. So starting on the left, the first thing is you have a counting number, except it's a letter. But the states are counted because, for instance, you have a doublet pi state. I was going to say there may be an infinite number of them. I'll rephrase that. There are an infinite number of them. For a neutral system, you have an infinite number of states, every symmetry below the ionization potential. So very sensibly, if you have an infinite number of states, you label them with letters, of which there are only 26. So there's already a logical problem in the convention here. And theorists tend to resort to using numbers rather than letters, but the experimentalists like letters. And the convention is the ground state is always called X. So that's easy bit, and that one's always obeyed, so remember that. Then the excited states go A, B, C, etc. up in order, with capital letters if they're the same spin state as the ground state, and lowercase letters if they're the same, if they're a different spin state to the ground state. Okay. Be great if it was actually observed. You can see already here we've got an A prime. Yeah, at least the other ones are in the right order. If you go to hydrogen, there's a E, F state. And that's because when the experimentalists first observed them, it has a double minimum in. Someone observed transitions to E, someone just observed transitions to F, and it took the theorists to calculate the curves to realize actually they were the same state. So it's very messy. Lots of inconsistencies, lots of primes and tildes and strange symbols. You just have to learn it for the particular molecule. But in theory, this is the thing you're meant to obey. A, B, C, capitals for excited states for the same spin, little a, B, C for excited states for different spins. And for instance, the two excited states in oxygen I referred to are little a and little b state above the ground X state. So for the lowest state, it tends to be all right, but it does get a bit messy. So this is just a label. The other bits are actually symmetries. So the first thing is spin, which is exactly the same as the label you had on atoms. It's 2s plus 1. So doublet means you've got 1 unpaired electron, spin half. Triplet means you've got 2 unpaired electrons. Siglet means it's a closed shell. Then you have this notation, which is Greek letters as opposed to Roman letters. And my guess is your Greek is even worse than my Greek, and I didn't do Greek at school. But they're a map, and I think I have it on the next slide. They're a map, well, I'll do it here. They're a map from the Roman letters. That's right. Neat. Yeah. So if you remember, we had S, P, D, F, G. I think most people's Greek alphabet runs out about them. They map to sigma, pi, delta, phi, gamma, or in capital letters, S, P, D, G, F, G, go to sigma, pi, delta, phi, gamma. I don't think I've ever seen anything higher than gamma. And this is the total angular momentum. This is the projection on the z-axis of the molecule. So the molecule no longer has spherical symmetry. We're talking about linear molecules here because they're all diatomics. But it has a symmetry along the axis. So you project the angular momentum onto the axis of the molecule. And then you label it with the equivalent Greek letter of the SPD. So the orbitals are labeled like this, and the final states are labeled with the capital letters. sigma, and I noticed they're left off here. So, sorry, I should talk about degeneracy. So the sigma states are not degenerate. There's just one version. All the other ones are doubly degenerate. And they're normally split. I'm not going to go in huge detail on the splitting because it gets quite complicated. But normally, so actually if you have a doublet pi state, such as here, that actually means for each rotational level J, there are actually 4 states because you get a spin splitting, fine structure, and you get what's called a lambda doubling splitting from the pi state splitting. So you end up with 4 energy levels for each J. Right. I think that's on this everything we need to do for the moment. So then we need some selection rules, and I've already shown you them, but let's go through them again, having looked at these things. So delta S is 0. That should be all right. Lambda, and I gave you letters, but I didn't give numbers. Sorry. That's a gamma, not an F. So the letters, I already gave you sigma pi delta phi lambda correspond to sigma pi delta phi gamma correspond to lambda equals 0, 1, 2, 3, 4. And as I said, these are doubly degenerate. You can actually think of them as corresponding to plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. But in practice, you normally take the absolute value and don't worry about the plus minus. So the rule is that lambda can change by 0 or plus or minus 1. So sigma to sigma, sigma to pi, but not sigma to delta. Vibrational states we discussed, and rotations you know and love, that they change by 1. So if we go back to our previous 2 pictures, X state, if we go up here, looking at the transitions, the lowest excited state is this little a triplet pi. This is calcium oxide here. Is that an allowed transition? Shall I go around the room again? Where do we want to start? I think it's time for the back to start here. Gentleman in the far corner at the back there. Any idea whether X to this transition here? So to go to this state here, the A triplet pi from the X state, is that an allowed transition or not? No, that's right. And it's not allowed because the spin is changing. Okay, so that's not allowed. Go away. That's forbidden. The next state up is the B triplet sigma plus. Gentleman next door, is this allowed or not allowed? Sorry? This is not allowed either because it's also a triplet. So this has delta S not equal 0. Okay. Next one going up is A singlet pi. Lady with the nice silver flask. Is that an allowed or not allowed transition? That's allowed, absolutely. So we can go to the A singlet pi because the spin is not changing. The sigma to pi is delta lambda is 1. This is actually, these tend to be the strongest. Sigma to pi is the most common strong transition in a low-lying state. Lady next door to her, going to the so that was the A prime singlet pi. Going to the A singlet sigma plus state. Allowed or not allowed? Sorry? Allowed, yep. Also allowed, so these two are allowed. I've not dwelt on these pluses. You can get as well. They're pretty unusual. They're not unknown. The ground state of oxygen is the triplet sigma minus, but I'm not going to dwell on them too much. It's quite difficult to visualize where they come from. So in this figure here, you've got two of these electronic transitions are allowed. Carrying on where we are, lady in the middle row there, going from the X doublet sigma state in aluminium oxide to the A doublet pi state. Is that an allowed or a forbidden transition? So this state here is A doublet pi. We're going from X doublet sigma. That's allowed, exactly. Last one. Ladies are sitting in the corner there. We're going now to a B doublet sigma plus from the A, and this is a plus as well, from the A doublet, X doublet sigma. Is that allowed or forbidden? Allowed, yep, exactly. Sorry, B doublet sigma plus. So actually, I've taken two pretty much random molecules that happen to be ones we've worked on. But there is something quite common about this. If you have a closed shell, the lowest one is always going to be a triplet. Because you move one electron out into an empty orbital. And then we had Hunt's rules, if you remember, we briefly mentioned yesterday, which said if you get a singlet and a triplet, the triplet is always the lower energy. So the lowest transition here is always a forbidden transition. Or to put it the other way around, you always get a metastable state here. But they tend to dissociate by other means because molecules have other electronic states that do this sort of thing. And that's called predissociation, and we're not going to talk about that. Whereas if you have a doublet ground state, that normally means you've got one spare electron you can move around, and then you get a whole stack of doublet states, and they tend to be pretty much all allowed transitions. So whereas it was two random molecules, it's quite a typical situation. Okay, people happy with that? Should I carry on? Yep.
Overlap. So basically they could not very easily come to other state.
So indeed, you get all sorts of couplings between the states, the non-radiative effects, which of course, if you work in a time-dependent variation, so using MC to QDH, QDT for instance, you put a wave packet on here, you'll move between states. I do it time-independent. What that means is that couplings between the states and the wave functions get mixed. Yeah. But either way, these things are not pure electronic states when they overlap like this. And going back to the problem with assigning CAO, that was the major problem. The crossings were wrongly treated by the experimentalists. That you have several terms that can couple them, and the experiments have made an assumption of which term was coupling them, and when we calculated it, that term was very small, and there was another term was very big, and the other term had different coupling characteristics that coupled different states. So the whole thing was a mess. They've made a wrong assumption. Yep.
Temperature and pressure, would there be opposite effects in the movement of these curves?
So curves don't move. The curves are absolutely changed. Well, yeah, with temperature and pressure. What happens, of course, is that if you go up in temperature, you have to start considering the fact you're going to occupy these vibrational states. So you get transitions like this and like this. And of course, these vibrational states tend to sample a much wider range of the potential. So you get a whole lot more vibrational states here. So for instance, if this lowest thing was an allowed transition, actually from the ground state, it'd be quite difficult to reach it because you can see it goes right up there. When you get to the vibrational state, you can go straight into the ground state. So it changes the characteristics because of the change of the Frank-Condon factor mainly. Pressure effects on electronic states is a very good question. Seems to be not very much work on it. We had and I'll talk about this when I talk about the XML project, we've been trying to do pressure effects for the molecules we consider for astronomy. And as I knew nothing about pressure effects, we got two experts to come visit us. One of us, Gianna Buldareva, loudly affirmed that there were no difference in pressure effects in electronic transitions compared to vibration rotation transitions. And then gradually we're getting measurements seeping out, and they seem to be completely different. But that means there's no theory available for the pressure excited states. I mean, you actually worked on pressure effects. I suspect you didn't do electronic spectra at all. So the other person we had visitors was Bob Gamache, who came to visit us, who Bobby did a postdoc with. And he has very good procedures for doing vibration rotation transitions, and we were using some of those. But I think it's still an open question exactly what they happen with electronic states. But these electronic spectra tend to be optically thin, and then the pressure effects are not quite so important. They really matter when you're dealing with optical thickness, because it completely changes the opacity. Right, so I've just filled in the right answers there, which you already gave me. So that's all good. So I mentioned titanium oxide, and the reason why this is so important is, firstly, it's an open shell ground state, so it's a triplet delta state. That means let's back up a minute. Titanium is a transition metal. I think it has one electron in a d orbital, if my memory is right. So you get this, no, that's probably two because it's a triplet state. So you get these very complicated d structures where you can move all the electrons around the d orbitals. So you get all these other states where all you've done is move this electron around in the d orbital, and they don't change by very much energy. So this is 10,000 wave numbers here. So this whole region here is the infrared region. And then you get the more standard, when you're having to move between shells in the orbital, then you get these more standard ones. I'll show you iron oxide in due course. It's a complete mess. So this is quite challenging, and we can try looking at allowed transitions in here. I will, rather than going around the room, I'll just do them for you. So triplet delta, what color am I on? Red, that's okay. Triplet delta can go to triplet pi, it can go to triplet sigma minus, and it can go to triplet pi, but you can't go to triplet phi. Oh, sorry, triplet delta can go to triplet phi as well, okay? So we're allowed all that, because they're all delta L. So sorry, the one I've got wrong is this one. You can't do. You can't do that. So that's a forbidden transition, because that's delta L would be 2. So that's the one from the triplet delta, but then this gets thermally occupied as well. So you get transitions from the singlet delta that go to the singlet pi, and not the singlet gamma, because that would be delta L equals 2. And if you look at the singlet delta here, they can go to singlet pi, but they're not linked to either of these states below, so this is a metastable state as well. So you get really complicated spectra. So I warned you about iron oxide. I reckon there are 54 states there. I think 2 of them have been observed experimentally. We have regularly people asking us to do a line list for this. It's completely impossible for us to do, to do anything which I'd have any trust in whatsoever. You have to have couplings between all those states. It's a real mess. Put it another way, it's good to leave some nice scientific problems for the younger people to do after I retire. So that one will still be around if you want to challenge. So we have a nuclear motion program to solve these problems called DUO, and it's about 10 years old now. So I thought I corrected this. I think I corrected this on my talk for tomorrow. Let me just do a quick correction here. That was run by UK Research Council, EPSRC, and they closed it down. So all our codes are now on the XML GitHub. Who here has used GitHub at all? Anyone? Yep, a few hands going up, okay. So that's a big place for keeping codes for free. Actually, my master's students have to write a program as part of their master's project, and at the end of it, they have to make a GitHub page with their program on so we can mark the program. And they get marks on how nicely documented it is on GitHub, and basically if you can take it from the page and use the program successfully, or if it's just a whole dump of Python which you don't understand. So anyway, our codes are all on the XML GitHub page. Actually, when you get there, you'll find they aren't. In some cases, you just get a link to another page, but you can get them all through the XML GitHub page. Keep on forgetting to do this. There we are. So this is the problem we're trying to solve. So you have to consider all the sources of angular momentum, the final one, the L coupling, the S coupling, and the rotations. Sorry. So you end up having, actually it's a relatively simple to write down Hamiltonian, but the matrix elements are really quite complicated. And we use a basis function, which is a vibrational basis function, the rotational basis function, a spin basis function. The spin states are just virtual. They're just alphas and betas, like I was writing down earlier in the week. And then a electronic state basis function, they're frankly just virtual as well. We get the electronic state matrix elements out of MolPro and just shove them in the right places. But at least formally, we use a basis set looking like that. And there are actually different Hunt's cases for atoms as well as molecules, depending on the order you do the coupling. So we did LS coupling only for the atoms, but there is JJ coupling, for instance, so it's a different case. Because we use a complete basis, it doesn't matter what Hunt's case we use. If you do perturbation theory, which is what most people do, and you just take the leading H elements, it's entirely dependent on which Hunt's case you do, because if it's really a Hunt's case B, and you truncate on Hunt's case A, you get terrible answers. If we have a Hunt's case B case, and we use a complete basis set, it doesn't matter. Our quantum numbers aren't very good, but our energy levels are all fine. So you have this coupling here between the rotation, the spin, and the angular momentum to give you the final J here. So that's all good. Except there's one more source of angular momentum in our molecules. Anyone remember what it is? What have I not got on here? Sorry? Nuclear spin. We've already done this. So unfortunately, vanadium is a spin 7/2 atom and has a huge quadrupole moment. So I told you that vanadium oxide is really important. We couldn't do it without considering the nuclear spin. So we wrote, my former PhD student, Chen-Wei Chu, added the nuclear spin to this. So we got an even more complicated version of the code, which has yet another basis function here to allow for the nuclear spin. And we had to go through, and there are 5 different nuclear spin couplings, and you get yet another Hunt's case. I don't understand Hunt's cases for nuclear spins. And I have a new pH. So this actually only allows for 1 of the 2 atoms to have a nuclear spin. But I have a PhD student who's just started last month, whose job it is to make it for a general code for 2 atoms. So at the moment he's doing hydrogen, because that's a nice, well, relatively simple case with 2 atoms, and all the electronic curves are well known. But we will, in general, hopefully by the end of a PhD, we'll have a full nuclear spin coupled code. But this was quite a tour de force going through getting all the matrix elements and working them out. So let's move on. So we talked about calcium oxide. This is what the lowest electronic state spectrum actually looks like. And going up is the measurement with the assignments of the vibrational state. So these things, what you've got here are, these are vibrational bands. Sorry. Those are vibrational bands, and the conventional, quite often you write these as V prime, V double prime. They've written them as V prime dash, sorry, V, that's 1 prime, that's 2 primes, V prime dash V double prime. So 3 to 1, 2 to 1, 3 to 2, etc., going across the molecule. What you can see here, someone was asking me about this yesterday, about this sharp sides to some of the bands. They all have a rather strange structure that they all look a bit like this, with a completely sharp cutoff and then a slope on one side. And indeed, I had an American scientist who came and told me that our results must be all wrong because nothing in nature has a sharp cutoff like this, but actually it does, and I'll explain why. That's the next task we have to do. Right, so yeah, the experiment by Peter Bernard's group, that's our calculated line list. And this molecule actually, I used to say it's not been seen in space, but actually was observed about a year ago in the interstellar medium and rotational spectra. But someone used our line list to observe calcium oxide in a meteorite coming in the upper atmosphere. I have no idea how you take spectra of meteorites because you have to be pointing, have your spectrometer pointing in exactly the right place at the right moment, but no doubt people have ways of doing it. And they assigned calcium oxide spectra on the basis of our line list, so that was rather exciting. Right, so electronic spectra. So just going back over the WS selection rule, you do occasionally observe spin changing transitions. The lowest transition in CO is the Cameron band, and I have another PhD student working on that at the moment. And you get these band heads, and these band heads are these things here in the spectrum, which are a pronounced feature. So if you look at low resolution, we go back actually and just do this. If you think about this, if you look at low resolution, you might just see a spectrum like that. Basically, all you see is the band heads. That's quite a standard feature. So we need to understand where the band heads come from. And they come from the rotational structure. So I've got a lot of maths here, but I want to just say the general principle before we get on the maths. So the rotational structure you've seen so far is very simple. And it's simple because we've assumed that the rotational constant in the upper state and the lower state, either for a pure rotational transition or for a vibrational excitation, the rotational constant is essentially the same. And that allows you to cancel things out, and you get 2BJ type relationship. Because the going way back. Because these depend on, the rotational constant depends, basically, the mass of the thing is unchanged. It depends entirely on what RE is. And RE shifts. So that leads to rotational constants being significantly worse. And typically, this is a typical example where the excited states we talked are longer. So that means RE excited is greater than RE X. Okay? So the RE for the ground state typically is shorter. So B equals 1 upon 2 mu R squared, RE squared. So that means that B for the excited state is typically less than B for the X state. So the rotational constants are normally smaller for the excited states. That means the rotational levels are closer together for the excited states than they are for the ground states. So that's not always true, but it's the most common case. So if we go back here, to where I had the maths of doing this. So you have RE in the ground state is not equal to the excited state, so BE in the excited state, sorry, the ground state is not equal to the excited state, and typically B in the excited state is bigger. So just doing this for a P branch here, you get the difference now between, you have to consider different rotational constants. So that's the difference to what we did before we assumed the two rotational constants were the same. Yep.
Low resolution, then why do we need to worry if we have high resolution?
Well, you get more information from high resolution. Spectra get taken both ways. So you get high resolution where you resolve every single line. And for me, that's useful. I use those data. But quite often, particularly if you're using a spaceborne telescope, that you may only have a resolving power of somewhere between a few hundred to a few thousand. High resolution, maybe you want 100,000, 200,000. As I said, we can look at the sun from the ground with 1 million. So the features stick out in low resolution, or actually they stick out when you just have a relatively small amount of the sample, even high resolution. Then the individual lines may just get lost in the grass, but you still see the feature of the bandhead. Okay? So I mean, to give you an example, I did an analysis with astronomer Yakov Pavlenko of titanium isotope abundances in actually I think in Proxima Centauri, in the very nearby, it's the nearest star to us, and it's a binary. And it's an M dwarf, has a lot of titanium oxide in it. And all we could see were the bandheads. But you could see the bandheads for the different isotopes. And was able to then get an abundance, and ended up saying it was the same as the sun. But the fact you could do it was already interesting. And you could use our line list for doing that. So you end up with this structure where you have to consider the vibrational energy of the two states. So the change in the vibrational energy and the rotational energy of the P branch is given by the energy transition from your lower state to your upper state. So this is electronic energy plus the vibrational energy. And these expressions, the two rotations, and I'm just looking at this and thinking I've got some primes wrong here. Those must be single primes. So that you've got this change, and then I've rearranged it using the fact that J prime is J double prime minus 1 for a P branch. So I've substituted the J primes here, and you get this expression here where you get a sum of the rotational constants and a difference of the rotational constants. And this depends on J, and this depends on J squared. So typically you start off at low J with a standard thing, and then they get closer and closer together as the J squared term gets more important. And then when the J squared term gets big enough, they start going back the other way. Because of it depends on the sign difference here. They either spread out or go back, depending on sign distance. So always one of the two branches folds round. So you get a bandhead either at the red end or the blue end. So the red end is the low frequency end. The blue end is the high frequency end. So you always get a bandhead because of this turning point here. Whether it turns at J equals 3 or J equals 20, that depends on the details of the numbers. But you always get this feature that comes around. So it leads to transitions getting closer and closer together, then turning over and coming back through. So I have a picture better than the one I've drawn on the next slide. Sorry, I need to get rid of this. There we are. So this is nitrogen, ninth Earth atmosphere molecule, and you've got the R1s and R2s are consequences of fine structure we're not going to worry about. But you get these rotational transitions coming. So you've got one branch going off this way, one branch starting going this way, and then bending around, coming back the other way. And when you add that together, you get this classic bandhead structure on the top. So to look at a low resolution spectrum, This is carbon-2. Carbon-2 electronic spectra are fascinating. They have a prehistory that predates spectroscopy. So I think I started this course by telling you that spectroscopy started in August 1814. The first spectrum of carbon-2 is published in 1804. Just the person who published it didn't have a clue what they were looking at. They just said, if I put carbon in a tube with an electric arc going and it glows at this wavelength, and published the wavelengths, and it's this band. It's the so-called swan bands that you're seeing here of carbon-2. And yet, UNSW in Australia is assigning new carbon bands in the last decade. I think there's been 3 new carbon bands discovered by them. So this is a molecule with a 200+ year history of having its spectrum studied. But this is now relatively low resolution. You just see these features here with these bandhead type structures in them. And that's got CH as well here as CN. But it's just it gives you an idea of what this looks like at low resolution. And you get this then so that was a lab spectrum. This is the carbon star showing the absorption features against the star, rather similar with these asymmetric peaks caused by the bandheads. And that's our attempt to model it, which works pretty well with the bandheads in them. So now, if you look at it, so in general, electronic transitions are not terribly good for isotopes, but because these bandheads give you a sharp marker, they can be. So this is just our modeling of aluminium oxide. So this is using our XMOL line list just to model for aluminium oxide, difference of aluminium-26 and aluminium-27 on the bandhead structure. Because that changes the rotational constants, the bandhead is in different places, and that's a visibly different place. And that was exactly what we were doing with titanium oxide, except we were changing the titanium isotope structure. Right, I talked about this spectrum already. This is the famous CN interstellar spectrum. After 5 minutes, okay, good. CN interstellar spectrum with 3 lines, 4 lines. Well, not really, 3 lines that Hertzberg extracted a temperature from and said it was 2.7 Kelvin and had no meaning, no significance to this comment. And I told you that actually what he'd measured was the cosmic microwave background for the first time without realizing it. So you can see here the notation of P and R, exactly the same as we had for the vibrational spectra. These are all actually the 0-0 band. It's going to, because it's interstellar, it's absorbing, it's going to be cold, so it's certainly going to be ground state 0. It happens for CN that the strongest transitions for the ground state going upwards. So the vibrations are given like that. R2, P1, etc. is standard. R2 is missing. P1 means J double prime 1 to J prime 0. R0 means J double prime to J 1, 0. So you've got 2 states occupied, J equals 0 and J equals 1 in the ground state, not J equals 2. And that's how you get a temperature. 2.6 Kelvin. So we've done spectral coverage, and you've got rotations going through radio frequency, large molecules or heavy molecules, more than large, but large and heavy go together. Light molecules, diatomics coming out into the far infrared. You've got vibration, rotation, infrared wavelengths. You've got electronic spectra going. Actually, you do get X-ray electronic spectra, but that's different. You're blasting out an inner shell electron. But the sort of electronic spectra where you're exciting the valence electrons, the outer electrons, are in visible ultraviolet. So that's your understanding of the electromagnetic spectrum, and also tells you what you can observe from the ground if you're trying to do this astronomically. So that's the sort of molecules you may want to look at. A couple of atoms in there as well. Hydrogen, let's do that after the coffee break. Always, actually, it's not a special case here, but because I've done it as a special case for everything else, I've done it as a special case here, but actually hydrogen just has normal electronic spectra like anything else. So let's have our break at this point. Any more questions before we break up? Okay. Chai time.